I often think about what it would be like to be blessed with magic, to do anything the heart desires. I often think about how most of us wouldn't have access to it anyway. I'm then reminded of computers which can, in theory, do anything. PowerPoint is magic. I do not say this lightly. You can make fractals in it, it is Turing complete, and you can make springs go boing boing. One of my favorite videos on the internet is this talk by Tom Wildenhain. I once had to give a PowerPoint presentation for an AWM event. I had already shown the group PowerPoint's fractal prowess, and I could pluck another idea from Tom's presentation, but I chose to fiddle around in the garden, waiting for a fruit to drop. And it did. Let me have the honor to show you how you can use PowerPoint as a calculator, not for numbers, but for sets. A set is a collection of distinct items without any ordering. This is an evil definition for a multitude of reasons, but we shall carry this knife in our backs for the remainder of this video. I'm going to be drawing sets as these disks, which you might be tempted to call Venn diagrams, but I request your restraint. I'll come back to this point at the end of the video. On the left side, I'll give an example of sets using numbers, and on the right side, we will see the effect on this abstract annular picture. Much like how a numerical calculator requires numbers and operations, we will look at operations on these sets. First, the operation of a union merges the elements together while ensuring nothing repeats. The disks coalesce with each other, forming a continuum, a singular entity. Then comes the intersection, which offers refuge to those repeated elements. The extremities of the disks disappear, leaving only the common part. Then we are led to subtraction, which removes any trace of one set from the other. The common elements of A and B are removed from A. One disk takes a bite out of the other. And the order in which you write this operation matters. This is when I learned that the order in which you select the pictures in PowerPoint actually matters. This sort of subtraction has never sat well with me, for it favors a single set. A simple solution to this is the symmetric difference, or in PowerPoint parlance, the combine operation. It merges the sets, and if an element has a twin, both of them are thrown out. Finally, we have the operation fragment, which is a beautiful operation, but a friendly introduction will have to wait until we talk about Venn diagrams later. I want us to start small, the tiniest step we can muster. Let us show that these two definitions of combine are the same. I'll do the corresponding operations on the sets, creating copies if needed. I'll put this outline so as to align our outputs properly. I find the two differences and then put them together using the union. Oh, it's certainly what we got from combine before. Then, we take the union and mercilessly subtract the intersection. Oh, what do we have now? Another shape that looks like combine. This is what I'll call a proof, and any further discussion about this qualification has been relegated to the tail end of this video. We now do a proof for 3 circles, which I place in this peculiar manner. I feel the, "But this is just a Venn diagram, bro," rant boiling within your chest, but I implore you to suppress that urge. I'm a fan of the symmetric difference as it combines all 3 operations in a neat package. It satisfies this beautiful identity where the B in the middle just disappears. We find A combine B and then find B combine C. These two combined together give us exactly A combine C. It is time for our finale, which I call the bow tie identity, for you will see why. This is nothing too hard, but also not too obvious. I will now stop talking and let the sets dance before your eyes. Both shapes match up pretty well, and I'll call that a successful proof. Hey, thanks for sticking around. I really encourage you to open the Wikipedia page of set identities, pick whichever suits your fancy, and let the proof happen in front of your eyes in PowerPoint. If you want to stick around for the promised discussion, welcome to the back alley. There's two things I want to talk about before I let you be on your merry way. First, is this really a proof? In the same way that if I give you this identity for numbers, you can plug it into a calculator, the left-hand side and the right-hand side, and see that they are equal. This comes with a caveat that due to floating point errors, some digits after the decimal point might be garbled. In a similar way, while placing these disks, you might be off by a few pixels, which might make your shapes a tad bit different. And of course, if I had an identity with 100 sets, I would not be playing around with PowerPoint. A similar thing happens with Borwein integrals, which is this famous example that looks like a floating point error, but is a real property of trigonometric functions. But for 3 sets, such smaller issues are unlikely to occur. I talk about this more in the description. Second, why am I so hesitant to call them Venn diagrams? Venn's original paper discusses figures like this, but not in the context of set theory. He talks about statements like all x that are y are not z, which can be very well handled with these diagrams. Venn borrows the language from Boolean algebras, and he assigns each compartment cut out by the disks by points satisfying certain statements. For instance, this compartment contains points that are x and y, but not z. This gives 7 compartments in total, plus 1 corresponding to the endless void the sets float within. These compartments are exactly what the fragment operation produces. Venn's diagrams require all possible compartments to be drawn, and for more than 3 sets you can't use circles. Set operations act on only 2 sets at a time and do not capture Venn's pedagogical motivation. What was this motivation anyway? How do the logical puzzles come into the picture, and why did Venn negate the statements before using his diagrams? All of this is described in his paper, which we will talk about in the next video. See you then.